All right, Calc 3, welcome in. It's Thursday, September 16th, and it's the end of week 5. And welcome in. We are covering chapter 12. We're starting chapter 12. Remember, next week is our chapter 11 exam. It'll open up on Monday, and you can access it starting that. The 2 parts, talked about it last video, so check out that last video. For information about the exam. But we start with chapter 12 today, which is talking about vector valued functions. We really get into ways to track particles in space, right? Way to track particles in planes, in space, 3D space, and so on. And you're going to see that this is such a nice natural way of sort of saying, this is how an object is moving in my space. It's going to be much better than talking about just functions, right? Functions are actually quite limited. If you think of y equals f of x, it's super limited. It has to pass the vertical line test. There's only one output for every input, which means that you can't have curves that sort of go this way, right? You can't have a function that does that. In fact, circles are not functions, right? They don't pass the vertical line test, right? So we want to get to some sort of mathematical object that does make sense in how to point out how a particle is flying around in either 2 space or 3 space. And of course, vectors are the most natural way of doing such a thing, right? So let's get started with our stuff today. We get chapter 12, vector valued functions. I am going to use GeoGebra quite a bit because a lot of this stuff is visual as well. And so I created a workbook that is very nice for this topic. All right. So what the heck is a vector valued function? You're used to functions having a value, right? You plug in an input, a real number input, and you calculate the function formula, whatever it says, and then the output is a number. So you're used to input being a real number, the output being a real number. Well, a vector valued function changes that slightly. The input is still a real number. We'll call it t, in fact. The input will be called a t value. And the output will be either a 2-dimensional vector or a 3-dimensional vector. Right? So so we could say instead of y equaling f of x, right, where, x is a real number, you plug that in and you get y a real number, right? Here, we input t, a real number, and the output is a vector. Okay. One way to think of t is time. Time is often what we can think of as the parameter value, we call it. The input is now called a parameter. We want to avoid talking about x values and y values here because the vector is most likely going to represent a point in space, and with one single time t, there's going to be a description of an x coordinate and a y coordinate. For example, here's what we would say. We would define our function r of t. Notice I'm using the vector notation here. Instead of f of x, we have r of t. And this will equal, as an output, some function of t, f of t, times I, plus some g of t, j. And so the output of this vector valued function is indeed a vector. And you could, of course, use the angle bracket notation if you wanted as well. That's equivalent. And so basically, you're taking t and you're plugging it into this component and this component, and then writing it as a vector afterwards. Right? Of course, this is the 2-dimensional version. You can have a 3-dimensional version pretty easily. All you have to do is just, extend your vector. So f of t I plus g of t j plus maybe some h of t k. Like that. Right? That's another possibility. That would be a 3D version, 3-dimensional space. Right? Of course, you can use angle bracket notation here as well. Right? So at the very core of this, the input is a real number, and the output is a vector associated with that real number. Right? So instead of matching real number to real number, it's real number to vector. Cool. Okay. Now, how can I represent this? How can I use this? What good is this? What happens, right? So, for instance, let's go ahead and, for example, let's consider the vector valued function r of t equaling sine of t, I, plus cosine of t, j. All right, so that's an example there. And if I was doing this really old school, what I would do now, and especially if you have like no idea what to do and to get a sense of what this looks like, right? You start to plot some points. You start to pick t values, right? Pick inputs, calculate outputs, and then see if you can, how that graph, what that looks like visually, right? And so here we go. Maybe an old school way of doing this would be, let's make a little table. I can make some t values here, and I'm going to plug it into sine. I'm going to plug it into cosine, and then I'm going to create the vector sine, cosine, like that, right? And that'll be the output of my function, right? So suppose t is 0, right? Then sine of 0 is 0. Cosine of 0 is 1. And so with the time parameter 0, I'm associating with it the vector 0, 1, which is just j, isn't it? Right? That's just j. So if I was to plot this, right, I could go over here and say at the start of time, at t equaling 0, I'm pointing at 0, 1 right here. Right? Would you agree with that? This is the vector that's associated with t equals 0. T equals 0, I'm pointing here. See that? T equaling 0 is not represented on the graph, but I can at least take note that at this time, or parameter value, I am pointing at this specific point, 0, comma 1, 0, comma 1, right? And now I might ask, well, okay, what about another convenient time later? And I know this is, trig function, so maybe I pick like pi over 2 seconds, right? At pi over 2 seconds, where am I at? Well, sine of pi over 2 is 1, right? Cosine of pi over 2 is 0. So now, at pi over 2 seconds, where am I pointing? Well, now I'm pointing at 1, comma 0, which is just I. And so I've gone from pointing to here to pi over 2 seconds later, pointing here. Right, now this is at t equals pi over 2. Now remember, pi over 2 is the time. It's not the angle, right, that I'm making. Right, that's the parameter. So at 0 seconds, I'm pointing here. And at pi over 2, I'm pointing here. Some of you might be like, well, pi over 2 is up here. No, that's not what I'm talking about, right? I'm talking about at time 0, I'm pointing here, and at time pi over 2, I'm pointing here. All right? Continue this process, right? Maybe put time values in between here to fill in the details as you went. You might find that you'll get a vector pointing like this, and a vector pointing like this, and a vector pointing like this. And then you can quickly see that if I actually plot the vectors themselves, the arrows themselves, I'm going to get a really busy picture and maybe too busy. Does that make sense? So what we often do instead is just plot the point at which the vector is pointing. Do you see that? So instead of keeping track of all of the arrows, I might just keep track of this point and what it points to, and then draw that. That's what we mean by the graph of a vector valued function. It's basically a vector's, what it's pointing at. Keep track of what the vector has been pointing at as it moves around, depending on whatever formula you have, right? Now, to quicken this process, let's go to GeoGebra, where I made this worksheet here that we can work with here. So all I have to do here is click on this, and I can put in the I component, which ours is sine of. Now, GeoGebra requires an x because it doesn't like t as a variable. So what I do is put in sine of x here, and I put in cosine of x, right? Cosine of x, hit enter. And do you see this? This is saying that r of t equals sine of x I plus cosine of x j, but then replace the x with t. So it's just an issue with GeoGebra wants that input for the function to be x. Yeah. Okay. And here I have t equaling 0. So over here I can say what the minimum time is. T min is 0, and maybe the max time, this is a weird time, isn't it? But that's actually 2 pi. And so if you actually just go here and you type in 2 pi, like that, oops, I get that out of there. If you just type in 2 pi, TPI, and hit enter, it puts in 2 pi for you. And so now I can just have it graph where we're at, right? So here we go. If time is 0, I'm pointing at 0, 1, which we got manually. And then as time goes on, it's pointing at these sorts of values here. And there's a value really close to t equals pi over 2 seconds. And here we go. I'm approaching pi. I'm approaching pi time, 3.14. There we go. And keep going. This is going to be 3 pi over 2. And it's pretty clear what this is going to draw. This is going to end up drawing a circle, right? And now I can have it animate for me. So I don't even have to hold a button. So I just say animate on. And now it draws, right? So it cycles through the t interval from the minimum value for t and the maximum value for t, and then keeps track of what it's doing. Now, if you were to ask to graph this on the t interval from 0 to 2 pi, your final answer would be this, right? And you don't have to graph the vector. You would end up just having something like that, right? You can turn on and off the vector by clicking on it over here. See that? So it's nice to think of it, the vector is drawing this point out, but when it comes to the graph of a vector valued function, we just pay attention to this. Now, there's some interesting things that can happen here, right? So for instance, I'm going to make a slight change here. Let's now talk about sine of x squared, t squared, sine of t squared, and cosine of t squared. And let's see how that affects the graph. Okay? Now, I am going to graph from 0 to 2 pi, and you might notice that, well, look at that. It draws the same circle, but it draws it out differently. I would like you to observe how this gets drawn out. I'm going to animate it. The t is cycling through the same speed as it was before, and I want you to see if you notice anything different about this. Ready? Here we go. Yeah, take a look at that. What is different from this configuration? It's the same circle, but what's the difference here between that and the other one? Okay, let me pause that. And yes, repetitions. Yep, exactly. And if I go back to the old way, let me show you the old one. This is without the squares. This is just sine and cosine as components. And now I animate. Yeah, this certainly goes around once. Talk to me about the velocity, the speed at which it's happening. Right? What's the difference between the speed at this versus if I back this up and then go back to the squared? Okay. Go back to squared here. And now I'm going to, again, the t is cycled through the same exact speed, but what do you notice here? I notice that it seems to be accelerating. Yeah, exactly, accelerating. So this is really nice because with a regular good old-fashioned y equals f of x, we get a picture of what something is, right? Like it's a parabola, right? Or it's a straight line, or it's a circle, right? But we never got a sense of how it was drawn out, right? Was it drawn out with a nice constant speed, like we saw in the original? Or is it accelerating as it draws? Do you see how this sort of representation for position might be super helpful if you're trying to track stuff in space, like maybe orbits of a moon or something like that, right? Orbits of planets around the sun, right? Actually having a speed associated with or a velocity associated with how it's drawing out seems like really important information that we would want to capture. And it seems like a vector valued function might be the way to accomplish that. Yeah. Okay. Now let's tweak this a little bit. Let's start playing around with this a little bit. What if I did sine of 3x and cosine of 3x? Okay. And I'd love suggestions in chat as well on how we can alter this the next time. What do you want to see next in this? All right. So here's what sine of 3x, cosine of 3x. Again, all GeoGebra is doing is making a table and keeping track of where it's at, plugging in t into this function and drawing the vector that we're at and see what happens here. Okay, it looks like I have another sort of constant speed situation, but it draws it out 3 times in the time that it took in between 0 and 2 pi. It drew it out 3 times, whereas the sine of x and cosine of x only drew it out 1 time. Right? Let's see if we can follow that pattern, right? What if I do cosine, what if I change this sine of 3x to sine of 5x? I guess my conjecture would be, oh, never mind that. I guess my conjecture would be it'll wrap around 5 times. Is that true? Let's see. 1 time, 2 times, 3 times, 4 times. Yeah, 5 times. There you go. Now, for a moment, you saw a crazy picture, didn't you? This is where I want to go next. What if these were imbalanced? Right? What if sine was 5x and cosine was only 2x? Now think about what that means, right? Think about why I get circular motion at all here, right? Think about sine, right, is always outputting something between 1 and -1, right? 1 and -1. And what this is saying is that the I component, which is the horizontal component, is always oscillating between 1 and -1, right? So I'd like you to watch this drawing out this time, but now just pay attention to the x coordinate, as it goes, right? So if I now accelerate this, if I turn this on, right, I'm going to have, this is going to 1, -1, 1, 0, -1, 0, 1, 0, -1, 0, so on. It's acting like a sine function, right? The horizontal component, component of this dot is acting like a sine function, right? Now, on the other hand, the j component is a cosine of something. That's also oscillating from -1 to 1. And so the horizontal motion has to go from 1 to -1. The vertical motion has to go from -1 to 1. But because it's sine and cosine, they're out of phase with one another, right? So while this one has a y coordinate of 1, this has an x coordinate of 0, right? And so now when I do this and accelerate this, now we see both of those sines and cosines happening all at the same time. So think about that, right? If I go left and right at the same speed and now introduce an up-down motion in the same speed, right? I'm going to start doing something like this, and you sort of naturally turn into circular motion. You see that? Now, imagine if these were imbalanced, if this was like a 2x, right? So think about what that means. It's going to go around the circle, it's going to do the oscillation twice in the same time that it takes cosine 5 times. It wants to do it 5 times this way, or the j component, so sorry, wrong direction. So it wants to do it 5 times, 5 oscillations this way, while doing 2 oscillations this way. And so you get a funky graph, right? So now when they're imbalanced, you get something like this. See how it wants to go up and down much faster than left to right? See that? And that's because the inputs of sines and cosines are a little imbalanced, right? They're not the same. See that? right? And I can have all sorts of weird fun with this, right? If I do just x, right? That should mean that it really is slow going left to right, but still wanting to do 5 oscillations vertically, right? And so let's do this extremely. If I do 5x, what if I do 10x now? See, just basically more vertical oscillations. Oh, this is interesting, and it sort of redraws over itself. What if I end up doing like 11x? Oh, there you go. So now I get a sort of out of phase. All right, is anyone with me here in chat? What do you want to see next? What kind of components do you want to see? Do you want me to change these? Okay, you want to see some inverted things. You want to see ln of x. Great, 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 great. Yep, so let's do it. See what happens. Now, again, remember, all this is doing is literally plugging in the t value into this and then plotting the point. That's it. And you can see GeoGebra is a lot faster than I am at doing that. So yeah, let's start with this. Let's see. I'm interested in your sine of 1 over x as well. That's very interesting. So something like that. And then cosine of 1 over x. I'll do 1 over x squared next, because that's what you actually said. But let's go there. Let's see what that does. Now, notice at t equals 0, I have problems, right? And that's because when I try to plug in a 0 here, it's undefined, yeah? And so that's why it's not showing me anything for t equals 0. But I'll start this in motion and see what I end up getting. No, it doesn't want to. Nope, I broke it. Oh no. You broke it. You broke GeoGebra. It's frozen. Oh no. I don't like that. That's hilarious. That is funny. All right, let's see. I might have to close this out. Hold on one second. Yeah, it did not like that. Yeah, lesson over. It's like done. Yoda was like, I'm done. Oh, that sucks. I wish it did not crash on me. Okay, I'm trying to work this out. Oh. It didn't crash. It just took a long time to calculate. Oh, that's interesting. Let's see. Oh my goodness. I am not sure what's going on. That is hilarious. But it's super slow. It's trying to crank out something. Oh, and that's back to 0. And it's like, I can't do that. That's funny. I don't know. Anyway, let's tweak this a little bit. I want to see what I want to see what this is doing. Hold on. Okay, now it's frozen again. It really doesn't like dividing by 0. I don't blame it. Okay, let's get these fractions out of here before it crashes more. Okay, we're back to that. So now, let me do just 1 over x. See if that's an issue. 1 over x. And then, maybe 1 over x squared or something like that. Okay, that should work. So let's go ahead and put this in motion. The performance, terrible though. Must be because of all the extra stuff that I'm actually recording or doing in the background here, right? Let me just make sure my performance is okay with x and just x squared. It might be the division that's just choking on a little bit. Am I okay here? There we go. Yeah, it's fine with that. So yeah, just must be a division issue. All right. So there you go. You have x and x squared. You have x squared and x there. right? So again, R is just pointing to where it's at. And as time goes by, I mean, that could be totally what? The projectile motion of a rocket, right? Trying to get to orbit, right? I mean, it wants to get horizontal pretty quickly. And so it's trying to do that shape right there, yeah? All right, let's see. 1 over x plus 1, maybe. Somebody mentioned ln of x. Let's see what ln of x does. Oh, I made a typo. Okay. Yeah, I think it's because I'm calculating a lot of extra stuff in the background that it doesn't like it. It should be good, but there's a lot of calculation going on. I bet you if I stop this and if I did it sort of just me manually doing it like this, yeah, it's not bad, but it trying to animate it really. Let me pull back the curtain a little bit here, show you what's going on behind the scenes a little bit. I got all of this going on. This is extra stuff that we'll get to later. Yikes. Don't be afraid. Like, don't be afraid for real. But yeah, there's some extra stuff going on there. So that's why it's running a little slow. Okay. Anyway, I'd love for you to download this and to play around with it, right? Download this. And when you're trying to, when it says graph these on paper, maybe try that on paper a little bit, but maybe try it on GeoGebra or some other graphing software that you might have some experience with or whatever. But there's one way you can do that, right? You just type in the I component and the J component here, and you get a fair enough approximation of the curve that you're going to get, yeah? So let's see here. Let me get this back to something decently performance-wise here. So here's sine of x versus x. Yeah. Yep, that makes sense. Right? The horizontal has to go between 1 and -1. And the vertical is just the t value, right? So it slowly increases in height, but it oscillates as it does it, right? And you can play around with all sorts of different things here, right? You can change this, change that, all sorts of things, yeah? So let's see what else we got here. Let that run there. Yeah, let's make this change too. So if I go back to here, let's put a number in front of the sine cosine. This is another thing that will show up a lot. What if I do 5 times sine of x versus cosine of x here? Okay. And as you can see, I end up with an ellipse, right? That this is a drawn out with an ellipse there, right? See that? Now, can you figure out why that's an ellipse? Well, again, now the I component is stuck going between -5 and 5 instead of -1 and 1. So it has to go out to 5 and -5 horizontally while still just going from 1 to -1 and back again vertically, right? And so that literally draws out an ellipse in that way. So the numbers in front control that, right? So like if I did a 6 there, I'm going to get a not as eccentric ellipse, right? So this is, I wouldn't say almost circular, but this is more circular than the other one, right? And so this eccentricity is a little bit less eccentric, as we would say, yeah? But notice that if these were the same, now they're balanced and it would get me a circle, right? So these vector valued functions really draw, ellipses really well, circles really well, all sorts of other shapes as well, yeah? And again, if I change like this inside, I can change how one component gets drawn, right? So now here, as x gets larger, the oscillations in the horizontal sense get faster, but the vertical still has to keep its oscillation speed, right, if you will. All right, so all sorts of things that you can do. You should play around with this until you're tired of it. Yeah, awesome. I do have a 3D version, so let's see. We can do that as well. So let me stop this real quick. and open up. The 3D version does not have as many features to it. Let me see here. Yeah, there we go. And so this will draw out 3D vector valued functions. Same idea. You want to, you have your I component, your J component, and your K component, right? And then your minimum T value and your maximum T value. And then you can animate this, and then it draws the three-dimensional version, right? So all that is just drawing that out, keeping track of where that particle is going, right? Plug in the T value, plug it into the three components, plot that vector, and track where it's been, right? That's it. Now notice here, we have a cosine and a sine pair, right? And we have the K component, which is 2x. So what that means is when I look above, from above, it looks like circular motion. See that? When I look from above, it's circular motion because cosine sine pair gives me circular motion, doesn't it? These are balanced cosine sine pair, right? And so what if we did 2x there? Now, when I look here, look this way, look at this. That looks awfully like a sine function, right? Looks like a sine function. And when I spin it around this way, this looks like a cosine function. So you can see, if you look head on, right, you can start to reclaim the viewpoints from the three different components, yeah? But put all three together, and you get this spiraling up sort of thing here going on. What about cosine, sine, and tangent? Ooh, yeah. So if I did my K component of tangent, I'm going to get some issues because tangent's not always defined. But let's go there and see if it explodes. Oh, look at that. Love it. Remember I told you about tangents asymptotes? Right? By the way, if I look above, look at that. I still see circular motion because of the cosine sine pair, right? What you're not seeing is the height, right? And the K component is tangent, and that's controlling the height of the thing. And so when I look at it this way on the side, well, it looks like something going to infinity because at the asymptotes of tangent, yeah? Look at that. That's hilarious. That's funny. Love that. Yeah. What if I did 1 over x as the height? Right? So I still get circular motion because of the cosine sine pair, but now the height is squashed pretty quick because as x gets large, as t gets large, 1 over t gets really small. So this gets a height with that. Maybe a triple x squared. Ooh, okay. So I'm hearing you say maybe cosine of x squared. Sine of x squared. And 1 over x squared. I think that's just going to squash it faster. Oh, look at it go. Oh, nice. Yeah, that's the real Zoom. You thought you were on Zoom right now watching this lesson? Nah. Ooh, look at that strobe effect. That's fun. Mm-hmm. Do I dare put let's put a sign. Let's put a 4 sine of x as the height. Let me stretch this out. Instead of 4, let's do, it looks like I can do 20. 20. Right? So when you're working on this, I would love for you to play around with it, plug in different things, try different things, make it explode, right? We're not afraid of that, right? I mean, the worst will just damage your computer forever and, you know, You'll have to buy a new one, I guess. Oops. No, I'm just kidding. But anyway, try some stuff, right? Try some stuff. The worst you'll do is crash GeoGebra and have to like restart it or something, right? But what's really interesting here is I would love for you to be able to figure out why it's doing the things it's doing. And as you think through those things, you're learning conceptual understanding, you're learning visual. You're learning how to look at this, right? How to see what these things do. Yeah, it really forces you to think about what's the X doing, what's the I component doing, what's the J, what's the K component, and that's what we're really after here, right? I mean, yes, your book is going to ask you to sketch these on paper, but I don't know. I don't think that's as helpful. I'd rather you put this in there, justify why this is happening, right? And then start tweaking it and saying, trying to guess what that should do, right? Like if I change this J component to just put a 4 in front of it, what do you think that should do? What would that do? Now, remember, when I look above, see this circular motion? It's a radius 1 circle, right? So if I change the J component to be a 4 times sine, what do you think is going to happen? Right? I have a feeling it should make it a bit elliptical. Would you agree with that? Because the I component is just going from -1 to 1, but the J component now has to go from -4 to 4 in the same time frame. So I'm going to hit 4 on here and hit enter. And yeah, look at that. That's exactly what happened. Do you see this? Now I have elliptical motion, right? Like that. And remember, the x-axis is the red axis. So yeah, so the I component is only going between 1 and -1, and the J component is going between 4 and -4. See that? That's what I'm talking about. You should be able to sort of change some things around, guess what's going to happen, and you'll find some surprises, and sometimes you'll be right, right? And so play around with those as much as you can. Yeah, that is. I think it's a fun way to really look into vector valued functions. Yeah. So bottom line here, some of the common things that we will talk about is when these are balanced very nicely. So let me stop this for a sec. Let's go back to maybe this is 4 cosine of t. This is 4 sine of t. And the k component is, let's say, oh, that's cool though. If I keep it like that, look at that. I got like a tilted orbit. How cool is that? I got to see this in motion. Hold on. See, I distracted myself. I'm like, this is cool. So this is 4 cosine, 4 sine. So I should see circularity when I look from above. I do. All right. But then when I look this way, I should see it going between -20 and 20, which I do. Right? But there's such a range here, such an agreement here, that the time that it oscillates this is the same as the time it oscillates this way. And so it doesn't curve back on itself or anything. It's literally a tilted orbit. That's cool. I like that a lot. Neat. I think I just made the thing upside down, didn't I? Hold on. Where am I at? There we are. There we go. If you're ever lost, like that was just disorienting right there, you can right click and click on, you click on here, you get back to standard view. And it'll get you back here, which then you can rotate, and then you can stretch this. Holding shift while clicking on and dragging will actually stretch or squash your units this way. Anyway, yeah, so here is what we're trying to think about. If you have a sine cosine pair and then something like 2x, then you get a helix, right? So you get this helix pattern. So it's linear growth in the height-wise, and it's circular sine and cosine in the ij component, right? And so this produces a helix. And that's a common shape that this book likes to work with quite a bit. All right. Okay, let's get to how, so just some mechanics here of how we can work between vector valued functions and maybe work out what the shape should be, meaning converting it back to maybe like y equals f of x or a function like that. So let's see how those interact with one another. So, but yeah, download GeoGebra, man. It's so fun. All right. So now, here's a little task for us. We want to express the parabola y equals x squared plus 1 as a vector valued function. Okay. Now, there are infinite ways of doing this, right? But let me show you how most of the time we choose this, right? Usually the real easy way of doing this is you have to pick what the I component is and the J component is, right? We often do this. We'll let x equal t, right? And then y has to be t squared plus 1. Do you see that? So usually we call the x the t variable, the t parameter, right? And if x is the t variable, then y, because y has to equal x squared plus 1, y would then have to be t squared plus 1. So one possible answer to this is r of t equaling t I plus t squared plus 1 j. That's one way to represent this curve as a vector valued function, right? So that's one possible way, right? Now, you could have made a different choice. This is one answer here. You could say let x equal negative t. Okay. In which case, then y would then be t squared plus 1 again. Right? So this is another way of representing that curve. You're like, wait a minute, how can that curve be the same as this curve? Remember, it's all in about how it's drawn out. The end result picture of this is the same end result picture of this, but they're drawn out possibly differently, right? Why pick x to be very simple, right? Couldn't I do this? Let x equal sine of t. Oh, are you kidding me? No one does this. Well, sometimes we do. X equals sine of t. Then y might be sine squared t plus 1. So my vector valued representation now is sine of ti plus sine squared t plus 1 j. Now, I'd like to go to GeoGebra and draw all of these. What I'm expecting is that these should all draw the same graph of y equals x squared plus 1. By the way, that's a parabola, right? Shifted up 1 unit. Yeah, so I'm expecting an end graph to look like this, right? But the way that it's probably drawn out will be different depending on which representation I use, right? So remember, the way that we do this doesn't care about how it's drawn. It doesn't care about how it's drawn out. This is all about end picture. So you get to make the choices of how it's drawn out, right? Now, for test purposes and stuff, they'll probably tell you, hey, use this as a parameter, let x be this. So we all get consistent answers. Does that make sense? But in the real world, you can let literally x be anything you want, some function of t, and as long as y is that function squared plus 1, that's how they relate to one another, right? And you get the same thing. So let's now go to GeoGebra and take a look here. We don't need the 3D one, so I'm going to put this away. Okay. My poor laptop is like, what are you doing? Why are you running all of this Zoom stuff, the recording stuff, and making me divide by 0? What the heck? All right. So now, this is the first representation we had. We had t, which I have to type in as x, and t squared plus 1 for the j component. So let's go ahead and do that. Okay. And I'm going to let t range from 0 to 2 pi, but that's not going to be very convenient, right? Because that's going to just draw up that part of the parabola. What I should do now is maybe switch the t to go from like some negative value, like -10, to maybe 10, right? The 0 to 2 pi worked really nicely for trig functions and such, right? But now it's more likely to do this. So now let's animate that. And it's drawn out this way. Yep, that looks like a parabola, all right. In fact, if I wanted to, here, let's stop this real quick, get this drawn out. And just to compare it, I can just go down to the input here and type in y equals x squared plus 1. Right? And of course, it's drawn the graph right on top of that. See that? So in fact, like there's nothing there. This is the bottom graph, right? And you can see that this traces out that graph. See that? So that indeed is x squared plus 1, right? Now let's change the components. This was our second representation. This was negative t and x squared plus 1. Watch carefully how this is drawn out. Look at that. It's drawn from right to left. See that? The parabola is drawn from right to left instead of from left to right. I suppose that makes sense, right? Because t has changed its orientation from t to negative t. Yeah. This is the one I'm kind of interested in seeing here. So let's pause it. This is our third representation, which we did sine of t and sine squared plus 1. So let's see, parentheses, sine of x all squared plus 1. I'm very interested in how this gets drawn out. Let's see. Okay, very interesting. So it's drawing out the parabola, the parabolic shape, right? But it's only going from here to here. Well, that's very interesting. So I think I have to be a little careful. I can't pick whatever I want to do this. Let me amend what I said earlier. So let's go back real quick to the paper here. So there's an issue that I introduced here. Do you see how x is allowed to be any value of t, right? From negative infinity to positive infinity, and x then hits all values. When I make this happen, x equaling sine of t, I am really limiting what x can be. Do you notice that because x is now sine of t, x can only go from -1 to 1. So that's the only portion of the graph it'll draw out, right? So maybe how do I fix this? Maybe I do t sine of t. T sine of t. Now, would you agree that maybe I can now hit all values for x? And then, of course, I would have to do this t squared sine squared because I have to square whatever that is. So now here's my fourth representation of this, okay? And I want to see how this gets drawn out. I think I might have better luck with this time. Let me turn off the, where is my, yeah, let's turn that off. Okay. So you see what it's doing? It's only drawing that part between -1 and 1, the x value, between -1 and 1. And that's because I artificially restricted it by saying x is sine of t, which means it's stuck between -1 and 1. So now let's fix this, maybe. My proposed fix is this. Let's go now with t times. Okay, and this will be t squared times sine squared. T squared times sine squared. And now let's see how it's drawn out. Oh, yes. I love it. That'll eventually draw the whole thing, won't it? See how x is getting closer to 0, it sort of drops. But then as x gets larger, as t gets larger, it's going to swing further and further and further. Yeah. And so this is yet another way to draw out the parabola. Let me squash this so we can see. Oh, that's funny. Nice. So what if I did like 100, negative 100 to, oh my goodness. Now this is just insanity. I mean, that's one way to draw out a parabola, isn't it? That's one way to do it. Very cool. Okay, so I hope you got the point across here that there's many ways to represent the same function as a vector valued function, because there's an infinite number of ways one can draw out a graph, right? And so, yeah, so hopefully that makes a lot of sense there. Awesome. Now, let's see, what else can we do here? Okay, yeah, let's do some more of that. I'll give you a more difficult one here, and this one's in 3D, in fact. So let's try this. We have a perfectly lovely ellipsoid. In fact, it's a semi-ellipsoid. Oh, that's cool. X squared over 12 plus y squared over 24 plus z squared over 4 equals 1. And they are making z greater than or equal to 0. So that's an artificial that. Oh, wait, I need to read carefully. It says, sketch the space curve represented by the intersection of this and the parabolic cylinder y equals x squared. Oh, okay. Let's back up. We want to sketch the curve in 3D space represented by the intersection of the ellipsoid, semi-ellipsoid, with the cylinder y equals x squared. Then find a vector valued function to represent the graph. Ooh, okay. To represent, function to represent, spelling is tough. To represent the graph. Okay. So let's think this through a little bit, right? We have an ellipsoid. Okay. And we're intersecting it with the parabolic cylinder y equals x squared. Now, y equals x squared is a parabola, of course, right? But z is not mentioned. So z can be any height it wants to be. So it's like a trough standing straight up and down like this, yeah? And so now I want to think about how that would intersect an upside down elliptical bowl, okay? That's the curve that I want to describe, right? That can be tough, right? So in this example, let's let the algebra guide us a little bit, right? I think it makes sense to let the algebra sort of take us there, if you will, right? So I'm going to start with the same way that we did before. I'm going to let x just be t. I get to make a decision there. Let's make that decision and see where that takes us. Let x equal t, yeah? Okay. And what I'd like to do is try to get this to be an intersection of two curves here, right? So now let's play around with this a little bit. We get x squared over 12 plus y squared over 24 plus z squared over 4 equals 1. Now, wait a minute. If I want to intersect this with y equaling x squared, let's go ahead and put in this condition into this graph, right? If I plug this into this graph, it forces y to be a certain connection with x, which means I'm no longer considering the entire ellipsoid. Right? I'm no longer considering the entire ellipsoid. I am now forcing this relationship into this relationship. Yeah? And so now intersect this. So here's what I'm going to get. I'm going to get x squared over 12 plus, what is y equal to in the intersection? Y is x squared. So I now get x squared squared over 24 plus z squared over 4. And I'm in really good shape here. Do you see what just happened? I now know that I can call x to be t. So I can replace this with a t. I can replace this with a t. And then, since I have one more variable left over, I can just solve for z in terms of stuff with t. Then I have my relationship that I need. I have my x equals, my y equals, and my z equals. Ultimately, that's what I need to find. I need to find what my I component is, what my j component is, and what my k component is. Right now, I've just declared this to be t. What is y? Well, if it is intersecting this, y has to be t squared. So I already know what x and y have to be. The only thing left over is z. So now I can solve this for z, replace x with t, and then I'll get my form for z. So let's go ahead and do that. So I'm going to get z squared over 4 equals 1 minus t squared over 12 minus t to the 4th over 24. All right, let's see here. I think I'm definitely going to get a common denominator here because I want to solve here, but I want to also be careful when I do this. So let's get a common denominator all over 24. That's going to be 24 minus 2t squared minus t to the 4. And I believe this factors. I think this factors, which would be a beautiful thing. Z squared over 4 equals 4 t squared, and let's see, yep, minus 6t squared plus 4t squared all over 24. Okay. Now I can multiply by 4. All right, so multiply by 4. This will cancel this with that, leaving a 1 there and a 6 down here. And now, because I know z is positive by decree, I can safely take the square root and then take the positive square root. So this tells me that z equals the square root of 6 plus t squared times 4 minus t squared all over 6. Ooh, that's not the prettiest, but indeed that is a parameterization. And the t value goes from what to what? Oh, that's an interesting question as well. So let's see. Is there a restriction for t? Well, if there's a restriction for t, it's the same restriction that x has. Do you see that? So what kind of restriction does x have here? Yeah. Right, and let's see. Oh yeah, look at this. Because z has to be positive. Oh, this is trickier than I think. All right, go with me on this one. I'm trying to figure out if there's a restriction for t. Can t be like 7 billion? Can t be like 0? Can it be negative? What can t be? All right. Well, from this, it looks like t can be anything. From this, it looks like t can be anything. But check this out. We know z has to be positive, and this has to be defined. Yeah? So the inside of this must be positive. Well, that's good news. 6 plus t squared, always positive, no matter what t value is. But look at this one, 4 minus t squared. Do you see that if t, for certain value t, this could be a negative number. So here is the problem. I have found the issue with t. T cannot be anything it wants to be. It can only happen when this is greater than or equal to 0. Right? Which tells me pretty quickly that negative t squared has to be greater than or equal to negative 4, which tells me that t squared has to be less than or equal to 4, which means that t has to be between -2 and 2. And so that is my minimum t, and this is my maximum t. But the restriction was kind of embedded in there. It was sort of hidden, wasn't it? Right? And so that's an interesting way to think about that. You'd have to actually look at each thing here and see where was their problematic definition here. And this was the problem I could find. This has to be greater than or equal to 0. And so that means this has to be less than or equal to 4, which means that t has to be between -2 and 2. Let's now go to the 3D applet for GeoGebra here, and I'm going to graph that, see what that looks like. So let's open this up. Okay. Turn off the extra stuff here. So I just have the position vector. Now, let's go ahead and I'm going to put in the minimum t value is -2. And the maximum t value is +2. Okay. And the I component we came up with is t. So that's going to be x in GeoGebra. The j component is t squared, so x squared. The k component is square root of 6 plus t squared times 4 minus x squared, all divided by 6. I'm going to zoom in here. And now I'm going to animate. Okay, it's off screen a little bit. Let's scrunch this up. Let's scrunch this up. And let's stretch out the height a little bit. Right? Oh, and I'm not having it draw where it's been. Oh yeah, I am. There it is. Yeah, there you go. I wonder why it's not drawing out there. I have a little bug in the yeah, there's a little bug in the program. It's not drawing over there. Can I fix that on the fly? Let's see. I might. Hold on. Hold on, hold on. Yes, I can. Pause this real quick. What it's doing is it's drawing from 0 value when it should draw from the minimum t value. So this should be t min. There we go. I have fixed it. How about that? Fixed on the fly. Love it. You gotta love it. Here we go. All right, so this is the intersection of y equals x squared with the ellipsoid. You see that? Notice it's always above. And notice if I've looked at it from above, it should look like a parabola. It should look like y equals x squared. Sure looks parabolic to me, right? So this is looking like y equals x squared from above, right? And then on the side here, it looks like it's following the surface of an ellipsoid. Let me graph the ellipsoid and put that in here. So I'm going to ask it to graph x squared. I'm going to stop it from animating while I do this. Oh, shoot. Okay, hold on. Let's delete that real quick. Okay, here we go. I'm going to type in x squared divided by 12 plus y squared divided by 24 plus z squared divided by 4 equals 1. Oh, that's nice. That puts some context, doesn't it? Take a look at what's happening now. See this? When I put this in animation now, notice that you can clearly see that this is following the surface of the ellipsoid. Do you see that? And it's just the top part of the ellipsoid. So this is literally the curve of the intersection of y equals x squared, the cylinder, with the ellipsoid that was requested. Let me go ahead and type in the cylinder as well. Y equals x squared. And see that? Do you see how that is following the literal curve of intersection there? Nice. See that? So how do we do that? You get an equation for both of these things. You find a way to plug one of the conditions into the other surface. And then you make a declaration for what you want the parameter to be. Yeah. So I started off with, I had an equation for the ellipsoid. I had an equation for the cylinder. I wanted to intersect those. And so I plugged this condition into this to get here. Then I made just an attempt. You remember, there's multiple ways to do this. But then I said, well, what if we just let x be t? Well, then y would have to be t squared to make that true. And then for z equals, I would have to solve this for z to make sure that this is true. And so I did that. It was a little weird, right? It was a little weird. And then I was able to get a description for z. Then at the end, I figured out, oh, not all t values would work, right? There's a restriction in t inherent in this. And that was borne out by noticing this term underneath the square root. This term had to be 0 or positive for this z value to be defined. Yeah. So there we have it. Any questions with what we did there? We doing okay with that? All right. Hopefully you don't mind all the pictures and stuff. I think the pictures super help. I think seeing it, seeing this, even though it might look complicated at first, really puts context into what we were doing on paper, right? And so I really encourage you to really get good at some piece of software, right? In fact, you should look up whatever you want to go into, whatever industry you want to go into, if you do want to go into an industry or a commercial job or whatever like this, whatever your passion is, start asking people in that industry what software they use. What do they use? Do they use proprietary stuff that you can't really get access to? Do they use common commercial software? Do they use Excel? Right? So some jobs we use Excel to do all sorts of crazy things that you don't think of Excel doing, right? But they might be like, oh, we use MATLAB. Oh, we use Mathematica. Oh, we use Maple, right? Or we use something else, right? And so you'll want to get that information, and while you're in school, sort of play around with getting to know software, right? That's for you in that way. That'll get you a little bit of a leg up on other people who might not have been thinking about that, right? So think about what sort of software they use to solve problems, right? Mathematics software especially. And that might be interesting to know, so you can start learning that. If you don't know or have no idea where you're going, then learn something. Learn GeoGebra, right? You can get by with a lot of math stuff on GeoGebra, and it's free, right? And so you can sort of get that. And practicing playing around with GeoGebra is practicing at least baby programming, right? A little bit. It's not full-fledged programming, but it is getting a computer, trying to get a computer to do something I want it to do, right? And so that whole process is a good one to go through. Yeah. Awesome. Any questions with what we were doing there? All right. Now, let's get into, well, these are functions after all. And you might have learned in Calc 1 and Calc 2 that you can take the limit of a function. So I wonder what it means to take the limit of a vector valued function. Like, what does that mean? What does it mean to approach a vector, right? Because remember in Calc 1 when we were talking about limits, right? We were asking the question, right, in Calc 1, we were saying, okay, here's the function. The function may or may not be defined at a certain x value here, called c maybe, right? And you were asking, well, what does this approach when I approach from the left and from the right? When I approach from the left of C, when I approach from the right of C, what height does this approach, right? And in many cases, it approached, right? We could say it approached L, right? And a limit doesn't care what's happening at a certain point. It just cares about what's happening to the height as I approach it from the left and the right. Okay, so what does that concept mean in a vector scenario, right? What does that mean in that case, right? So let's see what we can say here. Suppose I have an origin right here, right? And I have a vector valued function. I'll draw one single vector from it. Here's r of t, and it's pointing right here. Okay. And let's say I know the path of this. It does something like this. Okay, so it goes this way. All right, so r of t is swinging as t changes, as time changes, as the parameter changes. This is swinging around and pointing at that path along the way, right? So now I might say, well, what happens as t approaches some time, right? Maybe t approaches some value, yeah? What happens here, right? Well, let's say that maybe I want to approach some vector L, right? And what I would say here is as t goes to some parameter value a, I'm getting copies of these vectors along the way, right? And so I'd like to define the limit in this way. The limit of a vector valued function as t approaches a is L, meaning that when t approaches its time value of a, that I'm approaching what L is pointing at. Right? I mean, isn't that the idea of a limit? It's not too terrible. It's the same thing as saying I want to approach a certain height as I approach the left and right of the input. So here my inputs are parameter values. My output is an arrow. So what I'm saying is as I approach t to a, I'd like this to approach some sort of arrow. And if that does approach a single defined arrow, then we'll say that that's the limit, right? In other words, another way to think of it is the difference between L and R, which would be this vector here. See how this vector here is the difference between R of t and L. So this is R of t minus L. I want this difference vector to shrink to nothing in the long run. So as this moves, this will shrink to here, shrink to here, shrink to here, shrink to here. And so what we want, right, we want the magnitude of that difference to approach 0 as t approaches a. Okay. Now, thankfully, that's about all the concept we're going to work with limits, because we're going to quickly go from limits to derivatives, right? So let's get to the real practical stuff. So enough of the concept here. Let's get to the practical stuff. How do I calculate the limit of a vector valued function? I have really good news for you. Super easy, as long as you know how to calculate a limit like in Calc 1. So the limit as t goes to a of a vector valued function is the limit of the components. So the first component, you take the limit as t goes to a of the component function f of t, and that's your I component. Then you take the limit as t goes to a of the other component, and that's your j component. So how do you take the limit of a vector? You just take the limit of each of its components. That's it. You do it component-wise. For space, you'll have 3 components. Yeah. So finding a limit of a vector-valued function is very, very, very similar to Calc 1 problems, except you probably have 2 problems in one or 3 problems in one. Right? So let's see. For instance, whoa. You were loud. TA, you were loud. You're supposed to be quiet during class. Oh my goodness. Oh my goodness. This is your therapy dog session right now. Enjoy. Oh, yeah. Yeah, yeah. She didn't want you to do a limit problem. Let's see. She wanted to stop you from that. She got excited about limits. Yeah. Are you excited about limits? Oh my goodness, you are? Oh my goodness, you're so excited about limits. Yes. You're like calculus dog. Yes, you are. Oh my gosh. Okay. Let me do a couple examples of limits and then we will be on our way. Yeah. So here we go. Let's calculate the limit as t goes to 2 of the vector 3ti plus 2 over t squared minus 1. Don't bark. No bark. The neighbor must be out or something. Plus 1 over tk, like that. All right. So the good news here is all you have to do is plug in into each component, right? So remember, the way to calculate a limit is try to plug it in and see if it's valid. In other words, use continuity. So the limit of 3t as t goes to 2 is 6, right? So far, this is good. I got 6i. Trying to plug in a 2 here is valid. This is totally valid. This is t divided by t squared, which is 4. 4 minus 1 is 3. So I get 2/3. So everything's valid so far. And then I try to plug in a 2 here into 1 over t. That's valid. So this one was as simple as just plugging in. And so this limit exists, and it's this vector. See that? So a lot of limit problems are quite easy. They can just be plug in, right? Now, on the other hand, you might have some limits that aren't just plug in, and you get a 0 over 0. Let's take a look at one of those. So here we go. Limit as t goes to 0 of t squared I plus 3tj plus 1 minus cosine of t divided by t k. So I want to take the limit of that. Again, I'm going to look at it component-wise. So when t goes to 0, what does t squared go to? Well, 0 squared. So I definitely get 0i. When t goes to 0, 3t goes to 0 as well. 3 times 0 is 0. Right? But here I have an issue. Trying to plug in 0 gets me the indeterminate form 0 over 0. Right? Cosine of 0 is 1. So 1 minus 1 is 0. 0 over 0. So I can use L'Hopital's rule. Right? Remember, L'Hopital's rule can be used if you have a 0 over 0 or an infinity over infinity when you plug in. So I'm going to apply L'Hopital's rule. L'Hopital's rule says that this should be the same thing, this limit, the limit as t goes to 0 of 1 minus cosine t over t is the same thing as the limit as t goes to 0 of the derivative of the top. So the derivative of the top is sine of t divided by the derivative of the bottom. Derivative of t is 1. And then you try to plug in again. And now I plug in t equals 0, and now it totally works. Sine of 0 is 0. And so this component is also 0. So this limit exists, and it happens to be the 0 vector. So this is 0, 0, 0. Yeah? That's the limit of that vector valued function. Okay? Now, if one of the vectors, if one of the components doesn't exist, the whole thing doesn't exist. So in order to a vector valued function for a limit to exist, all components must exist. So if you get fine in one, fine in another, but then undefined or does not exist in one of the components, then the whole thing is off. The whole limit doesn't exist. Even though it worked for 2 of the components, it has to work for all of the components. So let's take a look here at this next example. The limit as t goes to 1 of the square root of ti plus the natural log of t divided by t squared minus 1 j plus 1 over t minus 1 k. Right? Now, right away, you might work from left to right, But I noticed something right away. Look at this term. Look at this k term. As t goes to 1, I'm getting a non-zero 1 divided by something going to 0. 1 divided by something going to 0 is going to infinity, isn't it? 1 divided by small, small, small gets big, big, big. Yeah? And so right there, I can tell that this limit is not going to exist. So limit as t goes to 1 of 1 over t minus 1 does not exist. So that means I'm done. I don't even have to look at these other two components. I already got one thing that broke it, right? And so this whole limit does not exist. And I'm talking about this limit. This limit does not exist. The limit of this vector does not exist because the limit of this component doesn't exist. Okay? Hopefully that makes sense. Now, let's do this one because this one I think is a L'Hopital and it might be good for the review. So I'm already done with this problem, but you might ask, well, what's the limit of this? Just to remind ourselves how to calculate limits. So if I want to take the limit of ln of t divided by t squared minus 1, notice when I plug in 1, I get ln of 1, which is 0, divided by 1 minus 1, which is 0. So 0 over 0 means I can apply L'Hopital's rule. So I'm going to get the limit as t goes to 1 of the derivative of natural log of t, which is 1 over t, divided by the derivative of t squared minus 1, which is 2t, right? And I think I can simplify and then try plugging in again. And so 1 divided by t, that means a t's downstairs. Well, there's already a t downstairs. This is 1 over 2t squared. Now I can plug in 1, and I end up getting 1/2. So this component limit actually exists and is 1/2 j, right? And this is 1i. So the I component was totally fine. The j component was totally fine. The k component was not. It was undefined or does not exist. So the whole thing doesn't exist. Okay? That's how you handle limits, all right? And that's about it. That's it for 12.1. Next time, next week, we're going to get into how do I differentiate and integrate vector valued functions. And what does that even mean, right? Like, how do I differentiate an arrow? What does that mean? How do I integrate an arrow? So we've not been talking about calculus too much. We've been talking a lot about vectors. The calculus returns. We returned a little bit tonight with the limits. But now we're going to get into differentiation and integration, really cool stuff because it's very visual. And like I said, we can use GeoGebra to really visualize what's going on and really see things in motion. I think that's the key is you can see this happening in real time. And it's much better than me just graphing on a piece of paper and like you visualizing it, right? I can see it happening on the screen in front of me. So looking forward to next week and running that through with all of you. All right. So hope you have a great weekend, everyone. Take care of yourself. Hope you're catching up with your class. Hope things are going well with that. Let me know if you're struggling. Let me know if you have questions. But then otherwise, I will check in with you on Tuesday. Until then, everyone, be well and see you next time. All right. Bye now.